Welcome back. I wanted to say one more thing about example 16. When we took this limit as x approaches infinity of this function and got infinity, that just says that as x goes to the right, the graph is going up to positive infinity. So it doesn't tell us if we really have any asymptotes one way or the other. In this particular case, we would have a slant asymptote, it turns out, because the top degree is one more than the bottom degree. But the limit is not going to tell us that. It just says that the function goes up as you go to the right. Now let's go back to looking at example 17. So example 17 says the limit as x approaches infinity of the square root of 9x to the 6th minus x over x cubed plus 1. This one actually has a very funny looking graph, but we'll come to that in just a moment. All right, so we have this square root business that's a bit weird. If we think about our analysis, here x is approaching infinity, so we got to keep that in mind in our analysis. So here at the top, the leading term in the top, inside of the radical at least, is the 9x to the 6. So if if x is going to infinity, that one's going to be leading the show, and that's going to be going to infinity. The square root of that would still be approaching infinity, and positive infinity. On the bottom, we have the x cubed running the show, and that's going to go to positive infinity as x goes to positive infinity. So we have an infinity over infinity indeterminate form for this limit. All right, but what to do here? Well, we can divide the top and bottom by the leading term of the bottom, which is the x cubed. And let me write that up. We're going to divide top and the bottom by x cubed. And I'll take it kind of slow here. So what we're doing is we're dividing the top by x cubed, so we can write it as this fraction looking thing, and then we're dividing the bottom by x cubed, just so it doesn't look too much like a tower of fractions. I'm going to put parentheses. Now the bottom we can handle. That one you get 1 plus 1 over x cubed. But the top is a little bit uncomfortable because we have this radical that's guarding this polynomial here, and we can't really get the x cubed can't really access that polynomial because the radical's guarding it. But we can employ an old trick, which is we can rewrite x cubed using a radical. So here's what it would look like. So here we have the top radical. Now I'm going to rewrite this x cubed as the square root of x to the 6th. If x cubed is like the wolf, we're now putting the wolf in sheep's clothing so it can go in there and attack all the sheep inside the radical. What we did is we just rewrote it, but it's the same thing. Like here we have x cubed, but then the square root of x to the 6th is the same thing. Here we have x to the 6th. We can write the square root as the half power, and then x to the 6th to the half. There we would multiply the powers and give us back x cubed. So really, square root of x to the 6th and x cubed are the same thing. Or another way you can think about it is like this. If you have the x cubed and you apply a square and then a square root, those two are going to undo each other, and you just get the x cubed. And so, but what we want is we want to leave that radical there. So simplifying the inside, we get x to the 6th. All right. So now the x to the 6th can sneak its way into the other polynomial and simplify. So it'll become 9 minus 1 over x to the 5th inside the radical. The wolf has eaten the sheep. All right, so that's what the top is going to simplify to. On the bottom, we already said 1 plus 1 over x cubed. Make that a nice cube. And now we know the limit will work its way into all these little fractions, and 1 over x to the 5th will go to 0, 1 over x cubed will go to 0 as x approaches infinity. By the way, if x were approaching 0, this would be totally the wrong analysis, because 1 over 0 is definitely not going to be going to 0. It's only because x is approaching infinity that these little fractions are going to 0. So then we have the square root of 9 minus 0 over 1 plus 0. This part of it I'm just doing for extra emphasis. You don't really have to write this part. You can evaluate it in your head here. So we get 3. So the limit as x approaches positive infinity is 3. That would say that there's a horizontal asymptote y equals 3. It's kind of interesting here because there's also a horizontal asymptote y equals negative 3 just by the graph of the function. And if we were to take the limit as x approaches negative infinity of this, we'd have to figure out why it is that the horizontal asymptote is at negative 3. There's a little bit of subtlety with turning the square root of 3 into the square root of x to the 6. That's worked out a little bit more in the homework. Basically, though, you would have an extra negative in front because those x values are negative. Again, I'll reserve that for the homework, and if there are questions, we will definitely answer them in class. All right. Which goes for all of this. If you have any questions, feel free to ask in class, or you can reach out to me. I'm always happy to help. Okay, so let's look at another situation where we have indeterminate limits. We saw 0 over 0. We saw infinity over infinity. And we are now going to see an infinity minus infinity indeterminate limit. Infinities, again, are not specific numbers. So we can't just say infinity minus infinity. Well, that must be 0. Infinity is not a specific number. It's more of a motion of numbers going out towards infinity, so getting bigger and bigger and bigger. It's an action of numbers. It's not one specific number. So these numbers going to infinity could be going to infinity faster than these numbers that are going to infinity. So they could be growing faster than these numbers, in which case the whole thing, infinity minus infinity, could just be infinity. The distance between these numbers and these numbers could be growing. Or they could be spaced apart equally, like these ones are just 3 more than these ones, but they're both going to infinity. And there the difference could always be 3. So it's hard to know exactly what infinity minus infinity is going to result in, unless you do a little bit of work to figure it out. So here we have in example 18, the limit as x approaches infinity of x minus the square root of x squared plus 16. In this case, we have this is an infinity minus infinity case, because as x goes to infinity, x goes to infinity. And then as x goes to infinity, the square root of x squared plus 16 is approaching infinity, because the x squared goes to infinity. And even when you take the square root, that still blows up to bigger and bigger numbers, goes to infinity. So this is an infinity minus infinity situation. Now, it's hard to really know what to do here, because we can't just this is a common mistake, but you can't just take the radical and apply it to the x squared and then plus the square root of 16. The square root doesn't distribute across addition like that. You can try it out with some numbers, like try the square root of 9 plus 16, for example. And you'll see that that's not the same thing as the square root of 9 plus the square root of 16. So we can't simplify this, but we saw before that conjugates sometimes help with radicals. So let's see if that'll help us here. They can help us rewrite the form of the radical. What I'm going to do is write that whole expression over 1. You can always write anything over 1. And I'm going to take the top and the bottom and multiply it by the conjugate. All we're doing is flipping the middle term, middle sign. So instead of minus, it's plus. Or instead of negative, it's positive. Okay. On the top, we're going to get x squared. And the whole thing about the conjugate is that the middle terms are going to disappear. The outer and the inner cancel each other out, so those middle terms disappear. And then you have minus the square root of x squared plus 16 times itself. So in other words, squared is going to be x squared plus 16. These two are going to cancel each other out, or the two radicals sort of cancel each other out in a sense. So then on the bottom we have x plus the square root of x squared plus 16. Now here, the x squareds will be gone, and this negative is going to distribute into the 16. So we have negative 16 left on top. And now that the dust has cleared, we can see where we stand. Or sit, because you're probably sitting right now. Well, the situation has changed a little bit. Now we don't have an infinity minus infinity. Here we have a plus in between because of our conjugate. So we have an infinity plus infinity. Well, that's just going to be a bigger and bigger number. That's not indeterminate. That's going to be going to infinity. Like the bottom is going to be going to infinity in that case. So if you analyze this, well, the top is staying at negative 16 no matter what, and the bottom is going to be approaching infinity. Like the x goes to infinity, the square root part goes to infinity, and when you add those two infinities up, like a million plus a million, well, that's going to be 2 million. That's going to be an even larger number. So these numbers on the bottom are going to be blowing up to positive infinity. So overall, what is this limit going to turn into? Looking at our analysis. If you said 0, that would be correct. 0 because the top is staying at negative 16, the bottom is blowing up to a big number, and 1 over big is going to be small. It's going to be approaching 0 overall. Okay. That's looking like what we see here. As x approaches infinity, the graph is getting closer and closer to 0. All right. You can also get some sense by looking at this. You'll have to write out the full explanation of why this is, how you can figure this out algebraically. But intuitively, you can kind of see why these two functions are canceling each other out. They're both growing to infinity at the same rate, and the difference between these is actually shrinking down to 0. That's because here you have, let's say you have a million for x. Well, here you're going to have a million. Here you're going to have a million squared plus 16, which is basically a million. In fact, the bigger x gets, the closer this is to just whatever the x squared is. Like x squared is leading the show here. So, and then when you take the square root, you're basically going to get x. You're going to get some number that's very close to x. So when you do x minus the square root of x squared plus 16, this square root of x squared plus 16 is basically like x. It's getting closer and closer to x the bigger x gets, because the plus 16 is doing less and less work when x gets really large. And so the difference between these two is shrinking down to 0. Now everything's negative because the plus 16 is going to make this square root a little bit bigger than x, but that distance between those two is going to be shrinking to 0 as you make x larger and larger. Okay, well, this has been a long packet, and you're probably happy to come to the last example. It's 1 a.m. when I'm recording this right now. So I'm kind of happy to be getting to this last example too. So example 19 says, find the horizontal asymptote of y equals sine x over x, and use the Squeeze theorem to prove that it is a horizontal asymptote. All right. We didn't really state it, but the Squeeze theorem also works for x approaching positive or negative infinity. So I just wanted to point that out first. I'll write a little note here. Now, something else to consider is that if we try to plug in, so to find the horizontal asymptote, we have to take the limit as x approaches infinity. So we're going to be thinking about the limit as x approaches infinity. Let me write that down as a note too. So to find the horizontal asymptote, we're going to take the limit as x approaches infinity. And it says the horizontal asymptote, so it seems to be indicating that there's only one. So we only need to check x approaching approaching infinity. If it said, you know, any horizontal asymptote, we might have to check negative infinity as well. But those are the only two directions you can go checking for horizontal asymptotes. They're either going to be out where x is going to positive infinity or where x is going to negative infinity. Those are the only two cases for functions, at least, where you can have horizontal asymptotes. So we're going to be taking the limit as x approaches infinity of sine x over x. And if you look at what's happening here, as x goes to infinity, sine x is oscillating back and forth between 1 and -1. And that oscillation is really annoying when it comes to limits, because it's not really settling in on any particular number. Now we're dividing it by x though, so hopefully this x, which is blowing up to infinity, is going to help to overshadow this oscillating sign, and it looks like that's going to drag the whole fraction down to 0. So probably the limit here is going to be equal to 0, because again the top is not fixed, but it's and it's not approaching any particular number, but it's not going to be getting too large or too small. It's at most going to be 1, and at smallest going to be -1. But the bottom is blowing up to larger and larger numbers, 1 million, 1 billion, 1 trillion. And so overall these fractions are going to be getting really small, really close to 0. Okay, so that's going to be the horizontal asymptote. Let's actually draw the horizontal asymptote there. Horizontal asymptote is y equals 0. HA, horizontal asymptote. So then it says to use the Squeeze theorem to prove that it is a horizontal asymptote. All right, so to get the Squeeze theorem going, we would need to trap our function between two other functions. We already saw that for sine x, or trig functions like sine and cosine that have bounds, that's a good place to start. So here we have sine x trapped between -1 and 1. That's what the outputs of sine x are between. And if we divide all three parts by x, we're going to get 1 over x, sorry, -1 over x, sine x over x, and then 1 over x. One thing I should mention is that this is true when x is greater than 0. Which is the case, because x is approaching positive infinity in our example. Now if x were less than 0, if x were negative, well then you'd have to worry about flipping the inequality directions here, right? If you divide by a negative number, the inequality is going to flip. But if x is positive, if we're dividing by a positive number, the inequalities stay in the same direction. They don't have to switch. Okay, so now we can say that the limit as x approaches infinity of the bottom function, which is -1 over x, and the limit as x approaches infinity of the top function, which is 1 over x, both of those are what here? 0. Yep. Because the bottom is blowing up to infinity, the top is staying at either -1 or 1, and that shrinks down to 0. So, by the Squeeze theorem, the function inside, in the middle right here, the sine x over x, also has to go to 0 as x approaches infinity. And then, so you can say, so the horizontal asymptote is y equals 0. Here's our box at the end of our proof. All right, So we proved that it was a horizontal asymptote because we showed that the limit, using the Squeeze theorem, that the limit as x approaches infinity of that function sine x over x is equal to 0. So that's why we have a horizontal asymptote, y equals 0. One little side note, sometimes people think that horizontal asymptotes can't be crossed. Well, here's a horizontal asymptote that's crossed an infinite number of times. So it's crossed, it's double crossed, it's triple crossed. This poor horizontal asymptote is crossed an infinite number of times. It's vertical asymptotes that can't be crossed by functions. Because then it wouldn't pass the vertical line test. It wouldn't be a function anymore. Horizontal asymptotes, though, you can, you can cross those as many times as you want, even an infinite number of times. Well, congratulations making it to the end of this packet. This one was a doozy. This is probably the biggest packet out of all of them. But you're well on your way to understanding limits. And in the next packet, we'll take a look at continuity, which is a concept that involves limits and connects function values with limits. Thanks so much for watching, and pat yourself on the back, and I'll see you next time.